Welcome to section 2.4, Goodness of Fit. We break down the variation in our dependent variable y into variation that is explained by the regression equation and variation that's unexplained. We begin with variation. So variation is the sum of the deviations of y from its sample mean. And the first step that we're going to do in this manipulation is we're going to add and subtract the predicted value y hat I. And you recall that yi minus y hat I is equal to the regression residual e sub I. Then if I break this outer parentheses and square each of the individual terms and then put them in their own under their own summation sign, I get the sum of the fitted values y hat I minus y bar squared plus the sum of the regression residual squared plus this cross product term, 2 times the sum of the deviation of yi minus y bar and the regression residual e sub I. Now this simplifies to the first 2 terms alone. That final term on the right, the sum of y hat I minus y bar times epsilon I is equal to 0. And to explain why, we'll isolate that term now in the bottom equation and first break the parentheses on the left. So I get the sum of y hat I times the regression residual minus y bar times the sum of the regression residual. Now if I expand this out, you remember that in the multivariate case, y hat I is equal to b1 plus b2 times x2i plus b3 times x3i, etc., up through b sub k times x sub ki. So I've taken the definition of the estimated point y hat I and applied it. And I have this new equation that's on the right. Now, this is all equal to 0 by inspection. And the reason why is the OLS normal equations. You remember when we took the sum of the squared residuals and then we differentiated it with respect to each parameter to be estimated, b1 through b sub k, and set each of those derivatives to 0, we got what was called the OLS normal equations. The first one was that the sum of the regression residuals must be 0. That takes care of the term on the far right. And then we had that the sum of the products of e sub I times each of the individual x's, x2, x3, all the way up through x sub k, must also be 0. So because of this, what we can say then is that this entire expression must be equal to 0 by construction. Then, repeating what we have from this previous slide, we could describe the sum of yi minus y bar squared over all observations in the data set as TSS, or the total sum of squares. It's the total variation of y from its mean squared over the data sample. We can decompose that into RSS, which is regression sum of squares, and then the final term on the right, ESS, is error sum of squares. So what you could think of is that what regression does is it creates this orthogonal decomposition in the variation of y between what's explained by the regression equation and what is unexplained. The unexplained amount is the squared residuals, and the reason why RSS would be the regression sum of squares, notice it's the deviation of the fitted values y hat I minus y bar quantity squared. Now, r squared, which is the proportion of total variation that's explained by the regression equation, is RSS, the regression sum of squares, divided by the total sum of squares. So it's literally the proportion that's explained. What I could do is I could substitute in for RSS TSS minus ESS. So total sum of squares divided by error or minus error sum of squares, and then I get the familiar form of r squared that you perhaps remember from the prerequisite course. It's equal to 1 minus the proportion of unexplained variation. When an intercept is present in the regression equation, so in other words, there's a beta 1, in other words, in the true unknown population parameter, there is an intercept, and then we fit an OLS estimate b sub 1. If b sub 1 is present in our regression equation, then it's easy to show that r squared is bounded by 0 and 1. It cannot be less than 0, it cannot be greater than 1. If the regression, however, does not have an intercept, then you can show that r squared is no longer bounded. What that means literally is that the variation of the regression line could exceed the variation that's contained in the raw sample itself. And what Verbeek suggests we use instead of r squared when no intercept is present is what he calls the uncentered r squared. You'll notice the difference here is that we do not subtract out y bar. We don't have y hat I minus y bar or yi minus y bar, quantity squared. This is raw or uncentered. Now, r squared can equivalently be expressed as the square of the coefficient of correlation. In historic classical statistics, rho, the coefficient of correlation, was a very important parameter. The coefficient of correlation is equal to the covariance divided by the product of the standard deviations of both variables. So you'll see here what I have in the first line is literally rho squared. So rho is the covariance of y and y hat I, and then we divide by the standard deviation or the square root of the variance of y and the standard deviation of y hat I. Okay, so if I apply the square bracketed squared term individually to the numerator and the denominator becomes squared, and in the denominator we recover, well, the standard deviations squared become variances. And now, if I break, or if I multiply out the inner parentheses, so we have the product of the two parentheses, yi minus y bar, y hat I minus y bar. If I multiply those terms out, I get what I have now in the third line. Then, substituting for yi, y hat I plus e sub I, the regression residual. Okay, so I've made that substitution everywhere for y sub I. And then when I break that new parentheses around the substituted yi, you recall from the previous slide that the sum of y hat I times ei is equal to 0, so that term falls out. The sum of y bar times ei is equal to 0, so that term falls out, and then I have consolidation of like terms, and I get this new expression in the numerator. Right, the sum of y hat I squared minus 2 y hat I y bar plus y bar quantity squared. Okay, and then that whole term is squared. you'll notice that that inner term now is equal to the sum of the deviation of the deviations of the regression equation. So y hat I minus y bar quantity squared. And now that term is squared in the numerator, and it appears once in the denominator on the far right. When I simplify that out, I'm left with the familiar specification of r squared from the previous slide. We have regression sum of squares in the numerator. We have total sum of squares in the denominator. So the old-fashioned statistic rho, the coefficient of correlation squared, is equal to r squared in the sense that econometricians think about it as the proportion of explained variation in the equation. On stata output, you will also see r bar squared. And the reason for r bar squared is that thinking about r squared, which we defined in the previous two slides, r squared is non-decreasing in explanatory variables. This should be a familiar result again from the prerequisite course. What this means literally is that if you add explanatory variables that lack any economic merit or meaning, r squared can never go down. At best, it stays the same, but if you add any variable, r squared in all likelihood will go up. That's what it means. R squared is non-decreasing in explanatory variables. Could be the same or go up. R bar squared is an attempt to statistically penalize the addition of explanatory variables that lack sufficient merit. And what we do is by dividing both numerator and denominator by their respective degrees of freedom. Right? You remember that the regression residual E has n minus k degrees of freedom. A simple deviation of y from y bar, since I'm only estimating one parameter y bar, that has n minus 1 statistical degrees of freedom. So if I adjust both numerator and denominator for their degrees of freedom, I get the formula for r bar squared. And r bar squared, if you add an explanatory variable that has little to no merit, r bar squared can go down. Okay. So, section 2.5, hypothesis testing. I was going to review again expectation operators. I know we talked about this in the previous lecture, so I'll go over this kind of quickly. If we have stochastic variables x and y, the expectation of the sum is equal to the sum of the expectations. For a stochastic variable x and a non-stochastic scalar a, the expectation of ax is equal to a times the expectation of x. So the non-stochastic constant can move outside the expectation operator. For stochastic variables x and y, the expectation of x over y is undefined. It is not equal to the quotient of the expectations. This can only be evaluated asymptotically, meaning as the sample size goes to infinity with the probability limit. And a couple more sections, I'm going to define probability limits, and we'll start doing that too. For stochastic variable x, the variance of x is defined in a mathematical statistics way as the expectation of x minus its expected value quantity squared. For stochastic variable x and non-stochastic scalar a, the variance of ax is a squared times the variance of x. For stochastic variables x and y, the variance of x plus y is the variance of x plus the variance of y plus 2 times the covariance of x and y. And if we have the difference of the two variables rather than the sum, the variance of the difference is equal to the sum of the individual variances minus 2 times the covariance of x and y. Okay, so a few results on statistical distributions. This is, again, supplemental to the text. I try in my lecture notes to follow as closely as possible the text, in this case for Bake, but this section on distributions is something that I've added, and it's just a summary of typical MathStat results that I thought might be useful to you if I put them all in one place. So if x is a normally distributed random variable with mean mu and variance sigma squared, then z, which is a transformation of x minus its true unknown mean divided by its true unknown standard deviation, is standard normal, meaning it's distributed normally with mean 0 and variance 1. That's very easy to show, and I think that's a homework problem again, or at least it should be. Easy to show that z is distributed normal 0, 1. If we apply this to a regression context, the OLS slope B2, if B2 is normally distributed with mean beta 2 and the variance given by the familiar formula sigma squared divided by the sum of xi minus x bar quantity squared, then B2 minus its true unknown value beta 2 and divided by its standard deviation must also be distributed standard normal. It's a simple application of the theorems that we've just covered. The chi-squared distribution is defined, what we could say is that if we have the sum of k standard normal random variables squared. Oh, actually, I should have added if we have the sum of k independent standard normal random variables squared, that gives me a statistic that's distributed chi-square with k degrees of freedom. So I stated it better in math. I'm better in math than words sometimes. If x is distributed normal, it's normally and identically distributed with mean mu and variance sigma squared, then the sum I equal 1 to k of the individual x's minus mu, the true unknown mean, divided by the true unknown standard deviation squared. So you'll notice now I have in the big round brackets a standard normal random variable. I square it, I sum it over k observations. This statistic is now distributed chi-square with k degrees of freedom. The applications of this, if we think about the true unknown stochastic disturbance term epsilon, if epsilon I is normally and identically distributed with mean 0 and variance sigma squared, then what I could say is that n minus 2, where n is the sample size, times s squared divided by sigma squared, the true unknown standard deviation, we can rearrange that and see that this is equal to the sum, I equal 1 to n, of E, which is the regression residual, divided by the true unknown standard deviation sigma, quantity squared. That is a chi-squared random variable with n minus k degrees of freedom. Note again that the degrees of freedom are n minus k, even though we have n residuals added up. And the reason why is that only n minus k of these residuals are linearly independent. And again, the exhaustive proof of this is in Schmidt's text, Econometrics, and it's in my office if you want to come by and take a look at it. The t-distribution is defined as a standard normal random variable divided by the square root of a chi-square random variable divided by its degrees of freedom. That's the definition of something that's distributed t. So, a simple first application, if x is normally and identically distributed mean mu variance sigma squared, and we have some hypothesized mean of mu sub 0, what I could say then is if I drew a sample with n observations and computed the sample mean minus the hypothesized mean divided by the estimated standard deviation. So remember, the variance of x bar is sigma squared over n. So S squared is the OLS estimator of sigma squared, the true unknown variance. So x bar minus mu sub 0 over the square root of s squared divided by n. If I start to manipulate this and show why this is distributed t, what I'm going to do in the first line of this expression is I'm going to divide both the numerator and the denominator by the true unknown standard deviation. So remember, my estimate of the standard deviation is the square root of s squared divided by n. The true unknown standard deviation is the square root of sigma squared divided by n. So I'm dividing both numerator and denominator by this true unknown value. What this gives me then in the middle line is, in the numerator I have x bar minus its hypothesized mean divided by its true unknown standard deviation. So that makes the numerator standard normal. Mean 0, variance 1. And then downstairs, when I manipulate the denominator from the first line into the second line, if I take the true unknown standard deviation and break that secondary denominator within the original denominator and move it back inside the summation, when sigma is moved back inside, you note what I have here is this sum of xi minus this hypothesized mean, mu sub 0, divided by the true unknown standard deviation sigma. So I have a standard normal random variable in the large round brackets squared, added up n times, and divided by its degrees of freedom, n minus 1. Okay. So I have then this now follows the definition of a random variable that's distributed t with n minus 1 degrees of freedom. Right? It's n minus 1 because x bar it has n minus 1 degrees of freedom. I'm estimating one unknown population parameter. The more applicable but more complicated application to what we're interested in is applying this to hypothesis tests about the value of the OLS slope B2. So with the normality assumption, right, so we assume that the epsilons are normally distributed, B2 is distributed normal with mean beta 2, variance sigma squared over the sum of xi minus x bar quantity squared. And suppose we have a hypothesized mean of 0. So, so the t statistic is B2 minus its hypothesized mean divided by its estimated standard deviation. So I'm going to go through the same playbook as I did with the previous slide. What I will do is I will divide both numerator and denominator by the true unknown standard deviation of B2. So that's with sigma squared instead of s squared. So I've divided that out of both the numerator and the denominator. So going to the second line, I've left the numerator unchanged, but in the denominator what I did, as I did in the previous slide, is I have moved sigma squared, I've moved sigma, the true unknown standard deviation of epsilon, inside the summation operator in the denominator. What this gives me then, in the denominator, I have the sum of EI divided by sigma quantity squared. So EI you remember the OLS residual has a mean of 0. I'm dividing by its true unknown standard deviation. So I have a standard normal random variable squared in the denominator. It has n minus 2 degrees of freedom. So what I claim then is that this hypothesis test statistic follows a standard t-distribution because it has a standard normal random variable in the numerator, and in the denominator we have the square root of a chi-squared random variable divided by its degrees of freedom. Okay. The F distribution is the ratio of two independent chi-square random variables, each divided by their respective degrees of freedom. So it follows this particular functional form. Although I should caution you that when forming a F statistic, be careful that the magnitude of the numerator exceeds the magnitude of the denominator. Right? So the F statistic should properly be greater than 1. Now, on to hypothesis testing. In general, a null hypothesis is constructed to describe a hypothesized state of the world. So this test statistic is constructed, so we construct some measurement of how far the real world deviates from the world as it's described by the null hypothesis. Right? And we construct it in such a way that it follows a standard statistical distribution, whether that be t, chi-squared, or f. So the test statistic is constructed which follows a standard statistical distribution if the state of the world described by the null hypothesis is correct. The probability of observing a value of the test statistic is deemed, or if the value is deemed sufficiently small, in other words, this probability is less than some value alpha, then we say the null hypothesis is rejected in favor of the alternate hypothesis. In other words, we have observed a value of this test statistic that is so unusual if the world described by the null hypothesis is true that we conclude the null hypothesis likely is not true. That is, rejecting the null in favor of the alternate hypothesis. If that is not true, what we say is we fail to reject the null hypothesis. I can't estimate, or excuse me, I cannot state this emphatically enough. We are not accepting the null hypothesis as true. All we are saying is that we don't have enough evidence to dismiss it as false. Therefore, to state it precisely, we fail to reject the null hypothesis. A t-test can be a one-sided test or a two-sided test, depending upon where the density of the rejection region is placed. Because chi-squared and f statistics are squared, so in other words, negative deviations from the null hypothesis are squared, and squares are always positive, what that means is chi-squared and f statistics, by construction, are always two-sided tests. A confidence interval is the interval of all values of beta sub 0 k for which the null hypothesis of beta sub k is equal to this hypothesized value is not rejected. Okay? So, you state that again. A confidence interval is the interval of all values of the null hypothesis for which the null hypothesis is not rejected. So what we could say then is, if we construct this around the true, well, so in equation 2.50, what we have is a typical t statistic, right? So we have b sub k, the OLS slope, minus a hypothesized value divided by its estimated standard error. And that should be less than negative, that should be greater than minus the critical value and less than the positive critical value. Now, if I multiply all three terms of this inequality by the standard error, I get this next expression, right? And then if I subtract b sub k, the estimated value from all three, I've now constructed a confidence interval. So what I can say then is if I take my estimated value of the kth OLS slope, b sub k, impose a negative value on it, subtract t times the standard error, that's the lower bound of the confidence interval. If all those terms are now, and then what I can do is well, then if I add that same amount to my estimated parameter, I get the upper value, right? I used to have negative values everywhere, but if you multiply everything by 1, then you get the proper confidence interval. Right. So what we can say then is that in repeated sampling, alpha % of these intervals that are constructed will contain the true value beta sub k, which is a fixed but unknown number, and thus not stochastic. So to repeat again, you remember since beta is a Greek letter, that means it is unknown, it is non-stochastic, it does not have a statistical distribution, it has a discrete unknown value. So what we can say with a confidence interval, by constructing it in this manner, we can say that in repeated sampling, alpha % of these intervals will contain the true value of beta sub k. Okay. Now, linear model test of significance. At the top of stata output, the first test that's done is a test whether all the OLS slope parameters are jointly equal to 0. So in other words, that beta sub 2 and beta sub 3, beta sub 4, etc., up to beta sub k are all simultaneously 0. If all these true unknown population beta parameters, other than the intercept, are equal to 0, what that means is that the predicted value of the ith observation, y hat I, is just the sample mean. Or another way of stating this, what this would say then is that the regression sum of squares is equal to 0, and the error sum of squares, the unexplained variation, is the entire amount of variation in y. So the error sum of squares is equal to the total sum of squares. So that's the null hypothesis against an alternate that at least one of these betas is non-zero. So in other words, we do have a meaningful regression equation. So under the null hypothesis, all variation is unexplained. The regression sum of squares is 0, and the entire variation of y is pushed into the error. So we construct this test statistic, right, given down here. So we have the error sum of squares, or total sum of squares, right? The error sum of squares if the regression equation is worthless, minus the error sum of squares if we have a regression equation with statistical merit. So by imposing the null hypothesis that all the estimated slopes are equal to 0, that is imposing k minus 1 statistical restrictions. So the numerator contains k minus 1 restrictions, and in the denominator, the error sum of squares, if the regression equation has merit, so in other words, I have k minus, or I have a full k parameters that are being estimated, the degrees of freedom of the regression residual are now n minus k. So this statistic now is the ratio of two chi-square random variables, each divided by their respective degrees of freedom, and thus is distributed f. For any set of j linear restrictions on a model, what I can say is that the error sum of squares in the restricted model, where I impose my restrictions, minus the error sum of squares in the unrestricted model, that quantity divided by the number of restrictions divided by the error sum of squares in the unrestricted regression equation is distributed f, with j numerator degrees of freedom, where j is the number of restrictions, and n minus k denominator degrees of freedom. Now, my editorial addition here, this test is actually quite intuitive, because if you ignore the degrees of freedom that are over here on the right-hand side of the equation, what you'll notice is that this test statistic is measuring how much unexplained variation increases when the restriction is imposed, right? So ESSU is the unrestricted error sum of squares. This is how much variation is left unexplained by the regression equation without any restrictions. I impose restrictions and I get a new error sum of squares, which will be larger. So ESSR minus ESSU is the amount that unexplained variation increases when these restrictions are imposed. So if you ignore the degree of freedom corrections, what this test statistic is giving me roughly is what is the proportion that unexplained variation has increased when I impose this statistical restriction, okay, this set of restrictions. I think this is another test. This is another homework problem. You can show that this second test statistic based off r squared is numerically identical to the one constructed with unexplained variation. So this identical alternate explanation asks, by how much does r squared fall when I impose this set of multivariate restrictions, right? So think about the previous slide. If my regression equation lacks any merit, all my beta sub k's are equal to 0, what we're saying is r squared is going to fall to 0 if the proper regression equation is actually the sample mean, y bar. So in the previous slide, the test of whether all the OLS slopes are jointly 0 is equivalent to saying I impose this restriction and r squared falls from whatever value it is to 0. Now, another cautionary note, the restricted and unrestricted models must have the same explanatory variable and the same number of observations for this test to be valid. Okay. The general case, if we want to express this in linear algebra in glowing generality, consider a set of j linear restrictions imposed on beta such that r times beta is equal to a vector q. So for one example, say that I have this R, which is a 2 by k matrix. So and then we have the scalar values. Each of those is equal to in Q. So what I'm hypothesizing here is that the sum of a certain number of parameters in the first line is equal to 1, and in the second one we are hypothesizing that beta 2 minus beta 3 is equal to 0. Okay, so now applying the theorems from earlier in this lecture, if beta is distributed with mean, if B is distributed with mean beta and variance B, then the linear transformation of B, which is RB minus Q, must have a mean of 0, and the variance would be given by this quadratic around the variance of B. So it'll be R prime variance B times R. And we could say then that a quadratic built around RB minus Q, and that's given by the bottom line. So it's the linear restriction RB minus Q is equal to 0. And so we're taking the quadratic of that divided by the variance. And then all divided by J. This is distributed F with J numerator degrees of freedom and N minus K denominator degrees of freedom. The happy news, I'm going to repeat this over and over again as we go throughout the semester, Stata can easily compute this for you with the command test. So once you perform a regression and then you follow it up with the command test, this is the statistic that Stata computes for you. However, it's critically important to understand what it is that Stata is doing. Why does it have the statistical distribution that it does? And then you can evaluate whether this test statistic is appropriate for your particular sample. Finally, a p-value is the marginal significance level for which the null hypothesis is rejected. Okay? So in other words, if your p-value is equal to 0.04, what that says is the null hypothesis, you could reject the null in favor of the alternate at a 4% level of significance. Okay. Type 1 error occurs when the null hypothesis is incorrectly rejected. So in other words, what this means is the null hypothesis really is true, but you have observed a value that's highly unusual. Right? So the null hypothesis is honest to goodness true, but you've just observed a weird value. The probability of type 1 error is alpha, the rate at which you reject the null in favor of the alternate. Type 2 error is when the null hypothesis is false, but we fail to reject it. Okay. Type 2 error is a little bit trickier. Econometricians, in evaluating the quality of their models, sometimes compute statistical power tests. You would do this in Monte Carlo analyses. Statistical power is the probability that the null hypothesis is rejected when it is false. Right? So remember, type 2 error is when the null hypothesis really is false, but we don't reject it. Statistical power says what is the probability that when the null hypothesis is false, I really do reject it. And of course, that would be defined as 1 minus the probability of type 2 error.